Okay, so here's the second day of our patterns section here. Yesterday we talked about 3 different ways you can look at patterns, whether you list them, whether you make a table, or if you graph them. So this first sheet, which you should have a paper copy of these notes that you can follow along with and write on, is going to have us revisit that concept. Um, so the first item here is find the next number. So looks like they're subtracting 2 to get to the next number. So 3 minus 2 is 1, and we actually get a -1 for the next number. And so to describe that, we would say subtract 2 is a decent enough way to say that. And then when we look at turn the pattern into a table, one thing we could do is we can have our Y column be 9, 7, 5, 3. And then what we're going to do is just have our X column just be the whole numbers. Um, and then let's see, down here at the bottom, if we graph that, I'll just put a graph over here. So if we graph those over pairs, 1, 9 is about here, 2, 7, and I'm kind of approximating here, 3, 5, 4, 3. One thing we're going to notice though is once again these dots form a straight line. So that's kind of a unique characteristic about some of these patterns. So we did describe patterns by using lists, using tables, and using graphs, right? So today, now we're going to describe patterns by using a next now statement. And so the next now statement. I use the word next now sort of as a way to figure out the next term. So here's a pattern here that let's recognize what they're doing. They're adding a 5 to get to the next number. So in other words, the next number is going to be equal to 5 plus the now. So what that means is to get to the next number, I add 5 to the current number. And so let's see some of these as we look at more examples. The pattern on the next one is notice that they're multiplying by -1 to get to the next number. So 1 times -1 is -1. -1 times -1 is 1, and so on. So we would say this. We would say the next number is -1 times the now number. And then let's see. The third pattern here is they're subtracting 5. And so we would say the next number is equal to the now number minus 5. So this would be a good time to stop the video and see if you can do the last example. Go ahead and stop it. All right, so now we're going to have this is the next number. You may have recognized that we're adding 3, adding 3, adding 3. The next number is the now number plus 3. So this is one way that we can sort of verbalize the pattern that we see in some of these sequences. So on the next identifying arithmetic sequence, so we need to define what arithmetic means. Arithmetic sequence is simply when you add or subtract a number. Add or subtract to get to the next number. Okay, so if we go back, a great way to look at that would be if I look at these 4 sequences, there's 3 arithmetic sequences. This one is arithmetic. This one, second one is not. The third one is arithmetic, and the fourth one is arithmetic. The second one would actually be geometric, but we're going to talk about arithmetic sequences today. So when we see these arithmetic sequences, we're looking to make sure, let's see, it looks like they're subtracting 3 to get to the next number. So this would be -17 and -20. And your next number is now -3. So on the next sequence, it looks like they're multiplying by a number. They're multiplying by -2. 4 times -2 is -8. -8 times -2 is 16. So that means -32 times 2 is 64, and then -128. So this is not arithmetic, but we can use a next now statement The next is now times -2. On the third example, it looks like we're adding a 5, adding a 5, and adding a 5. So that means that our next statement is going to be now plus 5. And the next number in the sequence will be 26 and 31. Let's have you pause the video and see if you can identify what this sequence is. Go ahead and pause now. I hope you recognize that they are adding, well, what is the sequence here? Oh, they're multiplying by 3 to get to the next number. So then the next number is going to be 27 times 3 is 81, and then 81 times 3 is 243. And so your next now statement is going to be, your next is now times 3. Okay? So the original question was, identify which ones are arithmetic. There's only 2 arithmetic. The first one's arithmetic because we're subtracting to get the next number, and the third one is arithmetic because they're adding to get the next number. If we multiply to get the next number, it's not arithmetic. Determine if the sequences listed are arithmetic. If they are, find the common difference. So the common difference is what we're going to be looking at. Let's define that. The common difference is the difference of consecutive terms. And I'll show you what I mean by that. So what we have here is on number 1, they're adding 3, adding 4, adding 5, and adding 6. This one is not arithmetic because it's not the same number. All right, so this is not what we want. But look at number 2. This is going to be -2, -2, -2. They're subtracting 2 to get the next number. So that's what the common difference is. This common difference is equal to, just take consecutive terms. 9 minus 11 is -2. Or we could have done 3 minus 5 is -2. So the common difference is taking the term minus the one before it. On the third example here, we're noticing here that it looks like they're adding a half. If 1 plus 1/2 is 3 halves, 3 halves plus a half is 2, 2 plus a half is 5 halves. So this is arithmetic, and we're going to write down the common difference is 3 minus 5 halves. It doesn't matter which ones I choose, but 3 minus 5 halves is equal to 1/2. And this one, let's do another one. 2 minus 3 halves is also equal to 1/2. So the common difference of this pattern is 1/2, and once again, it is arithmetic. Let's go ahead and have you pause the video and do this example. So one way to look at this is if you multiply by 2 to get to the next number, that's the pattern. So this is not arithmetic, and so we cannot identify the difference of these terms. So writing arithmetic sequence in recursive form. Let's see, name by position example. The term, each number in the sequence is named by its position. What that means is this: T1 is equal to 5, T2 is equal to 9, that's the second term, and T3, T sub 3 is equal to 13. So this common difference is 4, all right, because 9 minus 5 is 4. So that means that T4 is equal to 17, and T5, the fifth term in the sequence, is 21. So we can get 9 by adding 4 to the first term, or that the second term is the first term plus 4. We get 13 by adding 4 to the second term. This is the second term. Or that the third term is the second term plus 4. We get 17 by adding 4 to the third term, or that T4 is equal to 4 plus the third term. We get 21 by adding 4 to the fourth term, or that T5 is equal to the fourth term plus 4. So if we generalize that, we get the nth term is the n minus 1 term plus 4. So you have just written the recursive form of a linear sequence. You need a rule and a first term. So state the first term, find the common difference, and write down the common difference as a rule. So let's do some examples. So let's try, we're subtracting 3 to get to the next term. And so the first term is 7, and then we're going to add that common difference of -3. So let's just check. Does T2 equal to T1 minus 3? Let's see. So does the second term equal the first term of 7 minus 3, which is 4? Yes, it does. And let's check another one. Does the third term equal the second term minus 3? So does the third term equal the second term of 4 minus 3? Yes, it does. So I will continue to do examples for you in this video. All right, so here's where we left off. So the idea is we want to find something called the common difference. The common difference is just found by taking terms. The common difference is found by taking 15 minus 5, which is 10. So they're adding 10 to get to the next number. So T1 is simply listing out your first term, and then to find the next term, we're going to be adding that common difference of 10. So one way we can look at this is think of it as if the third term is the second term plus 10. So another question would be, is 25 equal to 15 plus 10? And that checks out. All right, so here's a sequence where we have the first term listed as -2. And then the rule here, this recursive rule says we're adding 5 to get to the next term. So this right here is your common difference. So if we add 5, we'll get 3, 8, 13, and 18. All right, on this one we have the first term of 5.4, and your common difference is 0.3. So what this rule says is that here's your second term, here's your first term. To get the second term, I'm adding 0.3 to get to the next term. So that's 5.7, 6, 6.3, and 6.6. Let's have you go ahead and pause the video, and I want you to try to write down these terms in this sequence. So pause the video now. And so the first term is 1/4, and what this says is that the second term is equal to the first term added to -1/2. So if we take off a half from 1/4, we're going to get 1/4 minus 2/4, which is -1/4. If we take away 1/2 from -1/4, we get -3/4, -5/4, -7/4. One more example. This says find the seventh term in the sequence. So what we're going to be doing here is we're just going to be listing out -6 as the first term, and the second term is found by adding 15 to that number. So -6 and 15 make 9. And if we continue that pattern, we're going to be able to find the seventh term. All right, so I went ahead and added that up to the consecutive terms. So here's T1, T2, T3, the fourth term, the fifth term, the sixth term, and the seventh term. So the seventh term would be 84. All right, and another attack that we can have with these sequences is looking at some diagrams. So the instructions here say, draw the next 2 pictures of the pattern, create a table for the first 6 terms, write a recursive equation. So what we have here is just a list of triangles that increase by 1. So the next picture is going to be a list of 5 triangles. And then the idea is we want to start with term 1, term 2, term 3, and term 4, and so on. And then we'll put down the number of triangles in each term. just about. That's like this example they did.